time to time, I give public lectures, and my very favorite part is the question and answer session that inevitably follows. The audience often comes up with interesting questions, but one of them sticks out in my mind. A young woman once asked me, "What is the weirdest physics phenomena that you've ever learned about?" Now, I don't remember how I answered her, but it got me to thinking, and I realized that I should have told her about a thing called quantum entanglement. It still blows my mind. Let's see if you agree with me. Broadly speaking, quantum mechanics is a physics theory that describes the behavior of atoms and even smaller particles. But quantum entanglement allows for weird quantum behaviors to be seen on sizes as big as people or even larger. So just what is quantum entanglement? In an earlier video, I talked about how the behavior of a subatomic particle, like a photon or an electron, is described by what is called a wave function. Brushing over many details, the wave function governs the probability that you will find the particle in a particular configuration. Before you make a measurement, you can't know, even in principle, what configuration the particle is in. To give a concrete example of what I mean by the word configuration, let's use the direction of the spin of a particle. Now, there is a quantum weirdness in that when you measure the direction of the spin of a particle, you first have to pick a direction, and then the outcome will always be either in the direction you picked or exactly opposite. It can't be anywhere in between. So, if you picked a measurement direction to be horizontal, the measurement of the spin direction could be left or right. It couldn't be up or down, forward or back, or any direction except for right or left. On the other hand, if you decided to measure in the vertical direction, the only outcomes of your measurement would be up and down. Left and right would be forbidden. It's certainly counterintuitive, but it's just a weird fact of life in the quantum world. Now, prior to the measurement, the wave function might say that the spin axis of the particle could be in any direction. Indeed, the most popular understanding of quantum mechanics says that the spin direction actually is in all directions allowed by the wave function. It's only when you make a measurement that the wave function collapses and the outcome becomes real. If you'd like some more information on wave functions and how they collapse, that other video might help. Now, what would happen if you had two subatomic particles? If you're like me, you'd think that they'd both be governed by an individual probabilistic wave function, and they'd be totally independent, with the spin direction of one particle having nothing to do with the spin direction of the other, and both of them being in all directions until a measurement is made. And that happens with four possible outcomes: two wave functions and two probabilities with all combinations of up and down. However, it's possible to prepare two subatomic particles so they both are described by a single wave function. That's what we mean by entangled: two particles and a single wave function. You do this by taking a parent particle, which in our example has zero spin, and let it decay into two particles. Spin is a conserved quantity, which means that it can never change. So, if the parent particle has zero spin, then the two daughter particles have to have opposite spin. If one has a spin pointing left, the other is right. If one is up, the other is down, and so on. When you add the two, you get the zero that you started with. So that's the simplest example of a pair of entangled particles, which is to say two particles with opposite spin and a single wave function that governs both of them. Okay, so now we're getting somewhere. The entanglement doesn't depend on the two particles being close to one another. As long as the two particles don't interact with anything, you can separate them by feet, miles, or even huge distances, and the two particles are connected by a single wave function, and the two particles will have opposite spin. Now, remember that one of the key facets of quantum mechanics is that the quantum world is intrinsically probabilistic. We can't know, even in principle, the outcome of a measurement before we make it. So, suppose we select one of the two particles and pick a direction to measure the spin. Say we pick horizontal. The measured spin will be either right or left, each 50% of the time. We could have selected the other particle to do the measurement with the same result, 50% right and 50% left. The real weirdness arises when we measure the spin direction of both of the entangled particles. Say we measure the horizontal spin direction of this particle over here on the left, and the measurement says it's to the right. Then we know that the outcome of the other measurement, it will be 100% of the time left, 100% of the time. That means that the information that one of the two particles had a measurement made on it was transported to the other particle. And here's the spooky thing. We can measure the spin direction of the two particles in quick succession, so quickly that we measure the second one before any conceivable information from the first measurement could have arrived. Let's be super concrete on this by remembering that the fastest thing in the universe is light. It travels a foot in a billionth of a second. Now, let's take two entangled particles and separate them by 10 feet. It will take light 10 billionths of a second to travel from one to the other. So now let's get tricky. We'll measure the horizontal spin of one of the two particles and see that it's to the right. Then, 5 billionths of a second later, we measure the horizontal spin of the other particle. We find 100% of the time that it's to the left. And remember that we did it so fast that not even light could have told the second particle the outcome of the measurement of the first particle. That means that quantum information can travel faster than light. Yeah, you heard me right, faster than light. That blew Einstein's mind, too. In fact, he co-authored a paper in 1935 with Boris Podolsky and Nathan Rosen that highlighted this problem. He also called this transfer of quantum information spooky action at a distance. This was one of many reasons why Einstein didn't like quantum mechanics. So what do we think about this phenomenon today? Does quantum information move at speeds faster than light? Yeah, it seems to. But it doesn't invalidate Einstein's theory of relativity because we can't control it. We can make both measurements and the outcome will seem random, and we'll only know that the two were opposite when we compare the measurements, and that information can be transferred no faster than the speed of light. So that saves Einstein's theory, which is a relief. Otherwise, I'd have to learn a whole new bunch of physics. But it's still perplexing. How is it that quantum mechanics can travel so fast? Well, there were some people, including Einstein, who thought that this wasn't so mysterious after all. Suppose that you had a red and a blue ball, but you couldn't look at them. You grab both of them and put them in boxes and separate the boxes. Later, you look in one of the boxes and see that it contains a blue ball. It will surprise nobody that the other ball is red. The answer was determined at the moment the balls were put in the boxes, not when the first ball was observed. And I admit, when I first heard about this, that was pretty much my reaction. The technical name for this more ordinary connection is called hidden variables. So the question is, how do we know that there is something new and different about quantum mechanics? How can we test the idea of quantum entanglement and compare it to the more intuitive idea of hidden variables? There is a long history of this, with a prediction in 1964 by theorist John Bell and a test in 1981 by Alain Aspect, as well as contributions by many others. I'm going to forgo the history and the details of the mathematics of the predictions and just explain the measurement. We know that if we measure the spin direction of one particle, that the other one will be in the opposite direction. But let's change it up. Suppose that we measure the spin of the second particle in a totally different direction. How does that change things? Let's measure the direction of the first particle in the vertical direction, but the second one in the horizontal direction. That means that when you measure the spin of the second particle, it will be either right or left. That's weird, but remember, that's how this works for quantum spin measurements. Now, I'm going to simplify the discussion by only talking about the situation when the spin direction measured for the first particle is just up. We could be more general and include both up and down cases, but it's more confusing, and the answer is absolutely identical. If you want to do the general case, let me invoke the phrase that physics professors love and students hate, which is, the exercise is left to the student. Okay, now let's get into both the quantum and hidden variable predictions. The first measurement is in the vertical direction, and it finds the particle has spin up. When you measure the spin of the second, you measure it in the horizontal direction, and you get right and left with equal probability. The first measurement gives you 0 predictive information about the second measurement. It turns out that both quantum mechanics and hidden variables make the same prediction for this scenario. This is very different from if you made the second measurement in the vertical direction, because if you did, you'd get a second measurement in the downward direction 100% of the time. Again, this is the same for both quantum mechanics and hidden variables. So now we're ready for the final bit, which is to look at all possible measurement directions for the second particle and see if the predictions are different for quantum mechanics and hidden variables. We will still assume that the spin direction measurement for the first particle is upward, and then measure the spin direction for the second particle, starting upward and then slowly spinning the measurement through 360 degrees. This graph shows the predictions of how often the second measurement will be in the direction the second arrow is pointing. If the second arrow is pointing upward, we know that the second measurement is always downward. So that means the second measurement agrees 0% of the time. If the second arrow is pointing at 90 degrees to the right, the second measurement can be right or left with equal probability. So it will be to the right only 50% of the time. If the second arrow is pointing downward, we know that the second measurement always is downward. So it is in that direction 100% of the time. And as we go to 360 degrees, the pattern is reversed. It's very important that we see that the predictions from hidden variables and quantum mechanics are different. This is key. So those are predictions. What does a measurement say? Well, these black dots show the measurement, and they are quite definitive. Quantum mechanics is correct, and the whole idea of hidden variables is completely ruled out. So, what does this mean? It means that the idea that the final measurement is already determined at the moment the two particles is entangled is false. It means that when you measure one of the two particles, the quantum information is transferred to the other particle at a speed faster than light. Now, with such a provocative statement, you can imagine that there's a lot of discussion. So first, the biggie. No, this does not mean that you can use this to transfer actual information. The collapse of the wave function is still statistical, and it cannot transmit a message. So sorry, we're still stuck with light-speed communication for practical matters. Another feature of this measurement is that scientists have thought very carefully about exactly what it means. There are some ideas, but all are weirder than quantum mechanics. And of course, nobody knows if these ideas are right or not. The bottom line is that, at a minimum, classical physics and hidden variables just don't apply in the quantum world. It's quantum mechanics all the way. The good news is that this new quantum interconnectivity can be useful in such things as quantum computing and quantum teleportation. Did I just come up with a topic for a future video? All right, this video was long, but there's a lot of counterintuitive stuff in the quantum world. And there's a lot more to learn, which is great because this is a thriving research field these days. If you like learning that we can definitively rule out classical intuition, please like the video and share it with your friends. And be sure to subscribe to the channel, because this channel is a place where you can come and hear about some of the most fascinating field of science there is, which is physics, of course, because, well, physics is everything.